welcome everyone for the training session belonging to work package 8. This one is on generators. To give you the basic background on operation of synchronous generators, and for that reason we'll start with working of electric motors, specifically permanent magnet and induction motors. My presentation will be more focused on physical background. We'll introduce some equations and underlying physical laws, and then we'll try to see why and how it operates like that. And then we'll, in the last slide, we'll also talk or implement this knowledge to understand, in addition, how synchronous generators work. For the start, let's look at three-phase electric systems that we all have. Please take time and see how it works. Maybe we can all look into that. Those who have your laptops will see better there. But please observe what's going on, for instance, here on the generator side. So the figure shows the three-phase system, the power plant, the generator. These lines here are transmission line system, and this here on the right-hand side is three-phase load, which may well be electric motor, induction electric motor. And please observe how one phase adds to the current, and how the flows go. Because we are kind of still used to thinking that we got from primary and secondary schools and numerous pictures that we see where we have a plus conductor or line going to the load, from the battery to the load, and then backwards. But you will see that in this particular case, this background or minus or ground wire is missing, and the other two phases take this role. So that's the beauty of the three-phase electric system. And you may also see that from the phase diagram. It's either for voltage or current. We have again three phases. Let's start with this green one, and then the blue one follows with with 120 degrees difference, and the red one in addition, so that's then 240. And then if there would be a next one, it would be then the same as the original green one. So for 360 degrees difference, that would mean actually that we are back again at where we started. And you may see that for this particular point here, the sum of the green phase and the blue phase equals to the red one, and it's 0. 2 times half, once minus 1 is 0. And this particular point, exactly at the start, blue one is 0, and the green and the red are approximately the same, just opposite, So that actually means that the net flow is always 0. Sum of these three phases always equals 0, and that's also reflected here. That's why we can connect them together, actually. This is something we are not used to. Just take a line, connect it to the ground, and you'll break the switch. It doesn't work in our real life, but for the three-phase system, when you have all the time free phases available, it's like that. So the sum of balanced, we say, system of all three phases, sum of voltages, is all the time zero, and that's what we call neutral conductor. And that's the neutral conductor that is in every plug which we have in our room. So neutral and one phase. And the voltage between the two is 230 volts. While if you watch carefully, you will see that between the phases, the voltage is actually bigger. It's not so easy to see because you have to think of RMS value, but anyway, it's in that case 400 volts. So phase to neutral is 230, and phase to phase voltage is 400. Okay. In our plugs, we have also ground wire, which is then just the one connected to the ground locally at the building. Well, this neutral conductor usually comes from maybe the last of transformers in a line leading to our houses. Okay, so it's a smart system actually. The next we'll see the three underlying physical laws: the Lorentz force, Biot-Savart law, and Faraday's law of induction. I will not talk too much on that. I will just say that these are the three. So the first one is Lorentz force. Lorentz force tells us whenever you have a current or wire with current flowing through it, inside the magnetic field B, you get a force on that. And that is already enough to explain how permanent magnets, electric motors work. And these are becoming more and more prevailing. So you may have it in your drill, or maybe in sewing machine, and maybe in clothes dryer or washer. So it's becoming more and more prevailing. How it works? Let's see. So we need magnetic field B. We need current with length or of length L flowing through it. That's a picture. Here in this picture, this white or bright things, these are permanent magnets. They are on the runner, rotating. And they create, obviously, magnetic field around it. And this magnetic field we denote with letter B. So that's magnetic field B. And this magnetic field obviously extends around the magnets. And then you have also the current flowing through this, what we call, let's say, static part or stators of the machine. And these have length L, and there is current I flowing through the stators. And they are turned on and off smartly so that you achieve maximum torque. So only Lorentz force, equation of a Lorentz force is enough for us to understand how such machine works. Again, permanent magnet creates magnetic field B. Inside the magnetic field, you have a coil, for instance, this one here, with length L, and you have a current I flowing through that, and then you get a force. Force acting on certain radius creates torque multiplied by omega. That's the power of the electric motor, either flowing in or providing on a shaft. Okay, that's it. And then you have two more laws which we need to explain how induction motor works. and that's this one here. So you need, in addition, Biot-Savart law, which tells you that that whenever you have a current that is being supplied by, I mean, it's a current flowing through a length coil or wire with length L, you get a magnetic field around it. I decided in this case to write the Biot-Savart equation in this particular form, but you may encounter other ways how to write it down. So, whenever you have a current flowing through a wire, you create magnetic field around it. And please remember, we'll explain that how a machine works, and that part will be used for explaining why the stator is arranged as it is. And the third equation that we'll use is Faraday's law, induction. You may remember that from high school. That's an experiment. Whenever you connect the battery and create a current flowing through this primary side or left side, then you create, according to Biot-Savart law, you create magnetic field inside this coil. And magnetic field is transformed through this loop and goes to the side. Now what happens? This particular coil on the right, the secondary, let's call it like that, feels that magnetic field was created or changed. It feels the change of magnetic field, and the equation tells you that whenever you have a change that is time derivative of magnetic flux, that is B times the area, you create a voltage here, but only when you change magnetic field, not that you have it all the time. So whenever you press the switch here on the left, on the primary side, you create magnetic field, and this secondary coil gets what we call induced voltage. This induced voltage then moves this what's called I mean, creates changes. You measure with the voltmeter change of voltage. Yeah, but then you keep it on the switch. What happens? No voltage anymore, you sense, because you still create magnetic field here, right? But you don't create the time derivative of magnetic field. So you have to turn on and off the switch if you want to have the voltage on the secondary side. So let's now use this knowledge to say or to explain how the induction motor works. So first you have three-phase electric system that you connect here, and you make it such that the current starts flowing along the coils, and you create a magnetic field using Biot-Savart law. So Biot-Savart law tells you that because you have current I flowing through the stator coils, which have length L, you get magnetic field. And what's very interesting is that this magnetic field is rotating, because you have voltage maximum, then you drop down to 0, you go to minus amplitude, and that kind of means that the magnetic field is formed and then dies out. And then the second coil, which is next to it, goes to the amplitude and creates a magnetic field near to it. And that kind of means that you have it, I mean, the magnetic field rotating inside. So rotating magnetic field is another class of three-phase electric system. So by connecting the three-phase voltage to the connection here, you create a magnetic field with which we denote by B, and this B magnetic field rotates around which the speed that we call synchronous speed. This is the speed of the generator rotating with maybe 300 per minute in the power plant or whatever. Synchronous speed they decide for. Okay, so magnetic field we have rotating inside. And then we have inside the magnetic field this stator. Now it's out, but you may imagine that you can put it in. Let's assume that in the beginning it's stationary, right? So what he sees, the runner itself sees large change of magnetic field because itself is stationary. And the magnetic field is rotating around and overtaking the runner or rotor. And therefore, this derivative is very high. And that actually means that on the bars of the rotor, a lot of voltage is induced. And this induced voltage creates a current flowing around the rotor, the bars of the rotor. And you have a lot of current running here around. And that means that you have everything you need for the Lorentz force. Magnetic field of the stator, B, I is the current running here around, and you have the length of this current inside the magnetic field, the bars of the rotor. Therefore, you get the force, you get the torque, you get the power. Okay? And then you run the induction motor. Slovenian word from Slovenia is not induction motor, is directly translated as synchronous motor. That means it only works when it's rotating slower with non-synchronous speed. And that means actually that it must be slower than the magnetic field inside. Because if it would rotate with synchronous speed, it wouldn't see or feel any change in magnetic flux. So this derivative here would be zero, and hence no voltage on the bars of the rotor, and no current, and therefore also no Lorentz force. So both terms, either asynchronous or induction motor, actually say that you only get induced voltage on the bars of the rotor if the rotor is rotating slower with asynchronous speed. And the more force you exert on the rotor, the slower it goes, and it responds with higher induced voltage and higher force. So the more load you give to the motor, the more torque produced. Of course, that cannot go indefinitely. Yeah. So that's the working operation of induction motor. It's a workhorse in industry. It has changed a lot the world that we are living in. And the third slide is about synchronous generators. Now let's move to this first slide. That was the induction motor from the second slide. Now we'll discuss what's going on here in the power plant as a generator. And I will use the generator that you like, driven by Francis turbine. Okay? So we have a Francis turbine runner here, and we have a generator here. And this generator is synchronous generator. And this means, and you will see very soon why, that you have to provide excitation current to the rotor. Remember, you want it to rotate with synchronous speed, so you don't expect anything I mean, you don't want that on the rotor, on the runner, you have some I mean that you don't get any voltage. So the excitation system provides now already the old-fashioned DC current to the rotor. So you always have a current flowing through the windings, and the current provides magnetic field around it according to what we call Biot-Savart law. That was the second equation out of 3. So let's have the turbine already in operation. It's running, and the turbine, let's say, is maintained so with variations of the flow rate of water flowing through it that it's running at the synchronous speed. And then you have excitation system supplied through slip rings to the rotor, and you have then the magnetic field B nicely rotating inside with synchronous speed. And then you have outside the runner, you have another set of windings, and these windings are what we call stator, and you guess already now probably that because they are stationary, there is a huge difference in velocity and huge change or variation or time derivative of flux. So you get a lot of voltage that is induced in the stator. And so that you see how it works. For instance, at the pump storage hydropower plant in the figure, bottom right, you see these gray wires or bars supplying current for the excitation system. And there is another set of 3, but you see only one of bars going up to the transformer and out, supplying power to the grid. So 6 wires, 3 going down, 3 going up. You have to synchronize the machine to the grid, obviously. You do that so that you first maintain or assure that there is a phase sequence on the generator the same as the external grid. Then you have to ensure the same voltage or match the voltage. You do that by what we call 0 voltmeter, measuring the difference between external grid and the voltage provided here. If you want to, for instance, increase the voltage here, what you do, you increase the excitation current. Sorry, not yet. You increase excitation current, you create higher magnetic field, you get more induced voltage. So by changing the setting of excitation system, you ensure that the voltage here is the same as for the external grid, and when 0 voltmeter shows you 0, then you are able, at least from the viewpoint of excitation system, to synchronize. And then you have to match the phase of, frequency of the turbine. You change the governor system, you allow more water to flow in if you want to increase velocity, rotational speed, or you close guide vanes, you have less water, it slows down a bit. So you match the frequency of the voltage to the frequency of external grid, and in addition you have to match the phase. So you may want to slow down a bit and then to accelerate to the speed that you have. And then you're synchronized. I understand you don't have synchronous generation in our project. That's something we'll have to solve, but that's the operation of synchronous generators. Just 3 slides.